finish our motion unit with two-dimensional motion. Two-dimensional motions, we have motion in both the x and y direction. If I drop a ball, it just goes straight down. It only has y motion. In this case, we're going to be throwing a ball maybe at an angle, and it's going to fly across the room, and it's going to go across the room, and it's going to go up and down. So it has x motion and y motion. And whenever you have that, you're going to split the problem into two parts, x and y. You're going to use the exact same equations, delta x equals v0t plus 1/2 at squared, for instance, but you're going to have to use it only on the x part or only on the y part. Here was one example. A boat travels at a speed of 8 meters per second east across a river that's flowing at 6 meters per second south. So I can kind of draw, here's my river. Okay, here's the boat. It's going to start over here, and it's going 8 this way. And the river is going at a velocity of 6 this way. And I didn't put it in here, but let's say that this river is 24 meters wide. And I want to know, for instance, how long it'll take to get across the stream, or how far down the stream it'll go by the time it gets to the other side. So I have to split it into x and y stuff. All right, for the x, I know the velocity is 8. I also know this distance down here, that's an x thing. So my delta x is 24. Put units on there, meters per second in meters. And for y, I know that the velocity is 6 meters per second. Now, this is a constant speed problem, so I know I can use this equation. And I can use that. I can't do anything with y yet, but I can use to find the time in the x direction. So plugging things in for the x direction, my velocity is 8 equals 24 divided by t. And if I cross multiply and divide, I'll end up with t equals 3 seconds. So now I know the time down here is 3 seconds. Now the one thing that is going to be the same for both sides is time. Time is a scalar, direction doesn't matter. So whatever time I have in the x direction, I'm also going to have in the y direction. Oh, now I can use this to find the delta x for this part. Use the same equation for y. This becomes 6 is delta x over 3, and when I cross multiply, I'll end up with delta x is 18 meters. So that was a pretty simple example, but if you didn't know to split it into x and y, and you tried to mix the 6 with 8 or something, you might get confused. Now, projectile motion, that's what most of this is going to be about. A projectile is an object that's fired into the air and is only under the influence of gravity. The trajectory is the path it takes. So, here's an example. Okay, if a bullet is fired from a gun and a bullet is dropped from the same height at the same time, which will hit the ground first? And it turns out that if we ignore air friction, and even if there is air friction, this is pretty much true, they hit at the same time. And I'm going to show you that in class. I have a little demo for that. But they're going to hit at the same time. So it doesn't matter that this bullet starts out shooting sideways and the other one starts with a velocity of 0 and just goes straight down. They're going to hit at the same time. So their vertical motion is the same, even though their horizontal motions are different. And the vertical and horizontal motions are independent of one another. And for all cases of this, the acceleration in the y direction is going to be gravity, so we're going to use -10. And once it's fired, there's nothing pushing it forward, there's nothing holding it back, as long as we ignore air friction, which would hold it back a little bit. In the x direction, the acceleration is going to be 0. Now, there are two types of problems we can do with this. Case 1 and case 2 is what I call them. Case 1 is when the projectile is fired horizontally. And it's going to be something like this. A ball is thrown horizontally with a speed of 12 off of a 20-meter-high building. Now, when I do these problems, my first step is always to draw a picture. All right. So we have this object that's fired straight horizontally with an initial velocity of 12 meters per second. Okay, the building is 20 meters tall. And we might want to know where it's going to land over here. All right. Now, we make a list of variables, but we have to split them into x and y. And look at what we're given. We're given this v0, that's the original velocity. That's all in the x direction. So v0 over here is 12 meters per second. None of it is in the y direction, so v0 for our y direction is going to be 0. This 20 meters over here, that's a height, so that's going to be our delta x. So our delta x is, but that's for the y direction, excuse me. Our delta x here is going to be 20 meters. I'm going to put a negative sign there because it ended up 20 below where it started. So I almost made a mistake and put that on the x side. If it's a vertical thing, we have to make sure we put it on the y side. Now, the accelerations we always know. Gravity is what pulls it down, so the acceleration over here is going to be negative 10. There is nothing pulling it horizontally, so the acceleration here is going to be 0. Now, whenever we have three things, we can solve using one of the equations. So I have three things on the y side. And usually what we're going to do is I'm going to solve for time first. So if we remember our equations, the one that has these variables in it is the delta x equation. It's kind of nice because with v0 being 0, 0 times any t is going to be 0, so this is 0 here, so I don't have to worry about it. And then I can plug in, we get minus 20 was our delta x, equals 1/2 times minus 10 times t squared. I get minus 20 is minus 5t squared. T squared is 4 when I divide, so then t equals 2 seconds. So that's the time, okay, over here for the y. Now, there's a couple things I can do. We might as well find the velocity here, okay, v equals question mark. So for our y stuff, the easiest equation now to use is going to be this one. V equals, the v0 is 0, I don't have to worry about it. Minus 10 times the time was 2, and I get minus 20 meters per second for the velocity. Gravity pulls things down, and they accelerate at 10 meters per second. So for every second, they gain 10 meters per second. So after 2 seconds, it's going to be going downward at 20 meters per second. Now, for our x side, the trick is I now know that the time here, because the time is the same for x and for y. So I might try to find the distance. So I'm going to use the delta x equation again. So this time my acceleration is 0, so this part becomes 0. And now I get delta x equals, my v0 for my x is 12, and my t was 2. So my delta x is going to be 24 meters. That means this distance right here is going to be 24 meters. It's going to land 24 meters away from the base of the building. Now I could also, if I wanted to, find the x velocity. I want you to see what happens with this. Okay, in this case, the acceleration is 0. So this part becomes 0, and I just end up with v equals 12 meters per second. And as long as there's no air friction, that's what happens. Horizontally, the speed stays the same. It stays constant. Now, case 2 is a projectile fired at an angle. So that might look something like this. We have a soccer ball kick with a speed of 20 and an angle of 15. So we're going to say v0 is 20 and an angle of 15 degrees. And then it's going to go up, and it's going to land over here someplace. Okay, so something like that. Now, for these type of problems, if I look at this initial velocity, it is neither an x thing or a y thing. It's a little bit of both. So I'm I'm going to redraw it here just so we can see it. V0 is 20. We got a 15-degree angle. And we have to split this up into V0 in the x direction and V0 in the y direction. So we got to use a little bit of trig. For x, since x is the adjacent side, I'm going to use cosine. So I'll get V0x is 20 cosine 15. So V0x equals 19.3. And our V0y, y is the opposite side, so I'm going to use sine for that, so it's 20 sine 15. And with that, I get a value of V0y of 5.18. Now when I make my x and my y chart, for V0 for x, I'm going to write 19.3. And for V0 for y, I'm going to write 5.18. Now, I got to figure something else out here. The acceleration is 0. The acceleration in the y direction is minus 10. Now, I do have to figure out one other thing with this problem. And that's going to be this. If I look at my arc right at the very top, okay, just like when we threw a ball straight upward, we said at the top the velocity was 0. Here it has a velocity, but it's going straight to the right here. So its y component of its velocity is 0. So I can say v equals 0 at the top for the y. Another thing you could use if you wanted to was here. Here, delta x in the y direction is 0. That's another possibility, but I'm going to do it this way for now, with v0 equals 0 at the top. Again, I'm going to find time first, and I'm going to use the y side in order to do it for this problem. So, this equation is going to be the one that's going to work for me this time. So, we got 0 equals 5.18 plus minus 10 times t. And if we solve that, we'll get t is 0.518 seconds. Now you have to be careful because that is just to the top. Okay? What do we do if we want to find the time for the whole trip? We would double it, and that's going to give us a time of 1.036 seconds for the whole trip. Now I can use that on the x side to find the distance. So x side, we're going to use this equation. Delta x is v0t plus 1/2 at squared. This is kind of nice because with an acceleration of 0, this whole part goes away. All right, and I just get delta x equals v0t. v0 is 19.3. And I'm trying to find the total horizontal distance, so I want to use the total time this time. So it's going to be 1.036. And when I multiply those together, I end up with 20.0 meters for the answer. So when you do these problems, it's important to know that you have to split things into x and y. There's a couple things that we're going to talk about. Acceleration is downward at all points. This is just gravity. Velocity is tangent to the path or the trajectory. So if I was to give you this, we're going to fire the ball this way, it's going to go up and come back down over here. And they ask you to draw the velocity or the acceleration at any point. At this point, the acceleration is still going to be straight down, and the velocity is going to be tangent. Here, velocity's here, acceleration's there. Over here, velocity's tangent, and the acceleration is down that way. Time depends on the vertical motion, or the y motion of the ball, and time is the same for X and Y. And we're going to see this probably in the lab. We're going to do the farthest possible distance is for a projectile launched at 45 degrees. If you launch it straight up, it's just going to come straight back down. If you launch it too flat, it's not going to be in the air very long, and it's not going to go very far. So the farthest distance is when you launch it at 45 degrees. And if you think of throwing a football or a baseball, that's about where you would let it go at 45 degrees to make it go the farthest.